All right, hello everyone. My name is Joseph O'Connor. For my final project, I built a venue image ranking pipeline. What does that actually mean? So I wanted to be able to take images from venues. This includes bars, restaurants, monuments, etc., and be able to rank them based on quality and associate them with different categories. These images include graphics such as advertisements, photos of the actual place or people in the place, as well as screenshots of mobile or desktop devices. So here are my objectives. The first one is figuring out what is a photo and what isn't. So I chose to try and classify a photo versus a graphic versus a screenshot. The second had to do with rating an image based on quality. There's two different ways that you can rate an image based on quality. You can do so with technical quality. This is something that's independent of the medium of the image. So like blurriness, noise, and compression. All decrease technical quality. You can also classify by aesthetic quality, which is how appealing an image is, or in this case, representative of a specific venue. Lastly, I wanted to encode an image to a word embedding of its category. So I want to be able to associate an image with a category and do so in a way with more context than just associating it with a orthogonal label. So let me talk about the data for a little bit. So I scraped Foursquare venue images, about 21,000 of them, all of venues in Manhattan, Brooklyn. They're 1 to 50 images max per venue. These images are labeled with a popularity score from 1 to 10, where 10 is the most popular and 1 is not very good. And they're also labeled by their medium. So they're mostly photos, and this was a problem. So I also brought in a separate data set called the IMP1K data set in order to get some screenshot and graphics to train on as well. The IMPK data set has their own categories, which I lumped into screenshot and graphics that you can see below. I also want to talk, excuse me, I do a lot of transfer learning in this project, and so I want to talk about indirect data that affects my pipeline. So MobileNet is a major part of this project. I do transfer learning on MobileNet directly, and then I also do transfer learning on models that do transfer learning on MobileNet. We all know that MobileNet is trained on the ImageNet dataset. There's also an image quality assessment model that implements something specified in a neural image assessment paper, which has two different models, one for that technical quality I talked about and one for the aesthetic quality I talked about. In terms of the technical quality, this company, Idealo, trains MobileNet and a fully connected layer to 10 output neurons on a dataset called TID2013. This dataset takes 25 images distorted in 24 different ways. For example, distorted by applying Gaussian blur to it. To 5 different levels of severity. This creates a data set of 3,000 images. Then they crowdsource scoring of 0 to 9 of all those images based on their technical quality. The other one is, it's the same model architecture, but this time trained on the aesthetic quality assessment data set. This is 250,000 multi-domain photos scored 1 to 10 by their aesthetic quality. So they could be landscape photos, they could also be photos inside somebody's house, for example. This is what I use to fine-tune on my Foursquare images, which I'll talk about more after I get to the architecture. So like I said, I was building a pipeline. Here's that pipeline architecture. Now the components you see in front of you, the squares you see in front of you are actually 2 different types. So one of which is called a component. And component's just a containerized compute resource that's isolated from other components, and those generate artifacts. Artifacts are just like a trained model, for example, or they're metrics over the training session of a model. So talking about this in terms of the objectives, this vertical column here of boxes includes components and their generated artifacts for the medium classifier. This one on the left has to do with importing the NEMA technical model, as I just mentioned. And this one on the right has to do with transfer learning after importing the NEMA technical model. Lastly, in this corner here, you can see everything that has to do with transfer learning the category encoder on top of MobileNet and the generated artifacts. There's also additional components, as you'll see, called like something dash upload, and those just have to do with deploying it to the Vertex platform so that we have to serve our pipeline. Now, some specifics to talk about in training. I'm just going to go over the highlights because I don't have too much time. With the NEMA aesthetic model, basically there's this idea that technical quality is independent of the photo subject, like you can distort all images with blur, but aesthetic quality is heavily dependent on what you're taking a picture of. So in that case, when I do, I have to transfer learn with NEMA aesthetic. I can just import directly with the NEMA technical. And then when I do transfer learning, I have another problem. And that is that I need to train with a different loss function than, say, cross entropy. This is because a score of 9 is intuitively a lot closer to a score of 8 than it is to a score of 1. And so I need to be able to take that into account when training the model. So I use Earth mover's distance as my loss function. And what this does is just measures the aggregate distance between probability distributions, and it works in this case. Now, some highlights for training the category encoder. So basically what I did is took MobileNet's convolutional layers, it chopped off their fully connected layer to 1,000 output neurons and replaced it by 2 layers, one to size 768 and one to size 512. Now, why 512? Because I use the universal sentence encoder to generate my word embeddings, and those word embeddings have 512 dimensions. And so that is what I'm trying to train for. Then why do I have 2 layers? I wanted to progressively decrease the layer sizes. I also wanted to have a deep fully connected net. And I did so because I noticed that at least all the autoencoder, the encoder portions of the autoencoder composers I found would progressively decrease layer sizes until they reach that center code size. Now, another thing that's unique about this is that I'm not training to learn output classes. I'm training to learn output embeddings, i.e. all 512 output neurons will be activated to different degrees for every class or every example's label, rather than just one being activated fully while the rest are equal to zeros. Again, this means we can't use something like a softmax output layer and use like cross entropy loss. We have to use something different. So I'm training directly to find these embeddings. And since these embeddings are normalized to a size of 1, I can actually go with cosine similarity loss. And that's the loss function that I use to actually train the category encoder. Now, moving on to results, I'm going to start with a medium classifier, and I believe this confusion matrix sums it up pretty well. So there's two big things going on with this confusion matrix, one of which is that the model is demonstrating a very big bias toward photos over graphics and screenshots. This makes sense because there are a lot more photo examples in the training data. One thing I would do next time is take a random sample of the photos that matches the magnitude of the amount of graphics and screenshots that I have, and hopefully that would eliminate said bias. The other thing is that the model is confusing graphics with screenshots more so than those with photos. This also makes sense. They are a lot closer intuitively. However, I think this can be improved significantly because human beings would be able to distinguish almost like with very, very high 95+% accuracy a graphic versus a screenshot. Okay, now the results from fine-tuning the NEMA aesthetic model. So initially I had an earth mover distance loss of 4.6, which decreased down to 4.2 after fine tuning. This is on the training data, all the data. So if it's not overfitting, then that's a significant 8.4% decrease, which would be significant for like a production results. So possible next steps, that would be very difficult to be overhauling the entire process, but would be useful would be to experiment with a model that can handle larger input images. This is because low resolution images, in my case, I use 224 by 224, actually inhibit the ability to discriminate on quality. This makes sense. If image is so small, you can't really talk about quality. Now, lastly, my favorite results to look at are with the category encoder. I apologize for being cut off. The average output, the true embedding cosine similarity of the category encoder was, and this is what's cut off, 0.57. So cosine similarity is a range between -1 and 1. So this is very significant, especially when you consider that the dimension of each of these word embeddings is length 512. Now, to get a more intuitive metric, I also made a custom accuracy function that I trained with in Keras. So there are 164 different category embedding labels in the training set. So this is how the accuracy metric works. If the nearest category embedding to the output embedding of the model is actually the true embedding label, then score it with a 1, else score it of a 0. So this means that we have a random guessing baseline of 1 on 164, or 0.61% of the time. So if our model has an accuracy around there, it's not doing much. However, the model has an accuracy, it's able to guess it 7.24% of the time. I think this is amazing. So this is 12 times better than random guessing in one sense. And if you think about it, this problem is even difficult for a human. Why? Because in the data, the categories that I'm using are not very orthogonal to begin with. It would be difficult even for a person to figure out whether an image is going to be of a bar or speakeasy, not knowing the bar or the speakeasy, or like the set of bars and speakeasies that you could choose from. It's also difficult even for a human to distinguish between my other example here, which is a bar and beer bar. So I have categories that are children of other categories. There are hierarchies, and you still have to distinguish between a child component and a parent component and hopefully get it right. This being said, a human being who would also have to do this problem would not be able to do it with, say, like 95% accuracy. It wouldn't be a trivial problem for them. And so that hopefully illustrates why 7.24% custom accuracy for me is a very satisfying results. All right. I know I ran through that very quickly. I apologize. I also wanted to include this bibliography page here. Thank you for listening to my presentation.